So welcome to our short video on when is a linear system having unknown quantities consistent. Our goal today is to investigate 3 different linear systems having unknown quantities in their coefficients. We're going to find values for the unknowns, which are usually represented by h and k, to make the system consistent. And we're going to explore also what h and k give the system infinitely many solutions. Okay. So our first example is number 23 from section 1.1. And we're just asked to find values for h that make this an augmented matrix for a consistent system. In other words, we want to figure out what h is going to make this system consistent. So when we look at the original matrix that's given, it looks just like this. And we identify our pivot, which is already a leading 1. We need to clear this column underneath this leading 1. So we're going to try to turn this 3 into a 0. Well, we'll use this pivot row as a helper row. We're going to replace row 2 so that we get a 0 in the first position. So it's going to be row 2 minus 3 row 1 will replace row 2. So row 1 stays the way it is. Of course, 3 minus 3 times 1 is a 0, and that was the point. 6 minus 3 times h is just the quantity 6 minus 3h. So suddenly things have gotten interesting. We've never seen this before. And then for the third entry, 8 minus 3 times 4 is 8 minus 12, which of course is negative 4. So we can already see that this system will only be consistent if this quantity is not 0. If this quantity was a 0, then we would have a row where 0x1 plus 0x2 equals negative 4. In other words, we would have an equation that says 0 is equal to negative 4. We know that's impossible. So we're going to try to figure out when 6 minus 3h is not 0. You might as well just solve for when it is 0. And we find out that happens when h is 2. So the answer is if h is not equal to 2, this system will be consistent because this quantity won't be a 0 and we'll be able to turn it into a leading 1. Now, although it's not necessary for this particular problem because it only asked us to find the h that make the system consistent, we could do a little more and find an expression for the actual solution. So I'd like to walk you through that now. If we were going to try to find the expression for the solution, we need to turn this into a leading 1. It's our pivot position. And of course, we would just multiply this row by the multiplicative inverse of this coefficient. In other words, the reciprocal, 1 over 6 minus 3h could be applied to row 2, and we'll replace row 2 with that. So again, row 1 is not going to change. Row 2, however, is going to look different. 0 divided by a non-zero quantity. Of course, the assumption here is h is not 2. Okay? You can see, this right here. We cannot have 2 down here. We'd be dividing 1 by 0. That's not allowed. So 0 divided by any non-zero quantity is still 0. 6 minus 3h divided by 6 minus 3h. Well, that was the point. We get a 1. And now, in the A23 position, we're getting negative 4 divided by 6 minus 3h. We're almost home. Okay? We're almost there. I'm just going to circle our pivot position. It's now a leading 1. And we now need to clear this column, right? So we need to clear above the pivot. Well, that means we're going to use this row as our helper row, and we're going to want to add something to h that turns it into a 0. So that means we're going to try to add a negative h. How do we get a negative h? We'll multiply 1 by negative h. So our row operation to clear that column will be row 1. That's the row that we're going to be replacing. So we write it down, minus h times row 2. That's going to replace row 1. Row 2 is going to stay just the way it is. I am going to write this slightly differently. I'm going to go ahead and just write this as 4 over 3h minus 6. All I've done is I've taken this -1, which was applied to the 4, and of course distributed it across the denominator instead. And it just simplifies that expression. Okay, up here we've got 1 minus h times 0. That doesn't change, and that's the nice thing about this way this works. H minus h times 1, of course, is 0. And now we've got to deal with this. It's going to be 4 minus, I'm going to use this expression instead of this one, h times this, because we're multiplying row 2 by h, and this is the entry. This is the same as that entry. H times this, so it'll be minus 4h over 3h minus 6. Now that is, kind of a piece of work, but it does tell us what x1 and x2 look like. We can simplify this expression because this is not very pretty. So let's go ahead and simplify that. So 4 minus 4h over 3h minus 6. I'm going to get a common denominator of 3h minus 6. So 4 needs to be multiplied by 3h minus 6. And of course, we've got minus 4h's already over 3h minus 6. So here we'll have 12h. Well, 12h minus 4h is going to give us a grand total of 8h, and then minus 24. So that's a little bit nicer. Okay. And we can see that our solution now is that x1 has this expression and x2 has this. And as long as h is not equal to 2, you can get yourself any solution. So given any h that's not equal to 2, we get a solution x1, x2 that could be written like this: 8h minus 24 over 3h minus 6, and then 4 over 3h minus 6. Again, we have gone over and above what was asked. We were simply asked to find values for h for which the system is consistent, and we have found that any h that is not 2 makes the system consistent. And now, when we actually look at the explicit solution, we can see, yeah, h equals 2 is no go, because that would put a 0 in the denominators of these two coordinates. But any other h value besides 2 yields perfectly good real solution. And we're ready now for example 2. So in example 2, the question is, for which values h and k is the system consistent? Here we're going to be given a system of equations. Okay, so we're given 2x1 minus x2 equals h, negative 6x1 plus 3x2 equals k. And we can see right off the bat that this yields an augmented matrix 2, negative 1, h, negative 6, 3, k. I like to label my variables above their columns just to keep myself sorted out and remind myself this is an augmented matrix, not just a coefficient matrix. All right, so a couple of ways to deal with this. We do recognize that we have a non-zero quantity in the upper left corner. That is our pivot. We didn't have to switch rows or anything. I could go ahead and divide this by 2, and clear that and make it a leading one. But you know what? I see that negative 6 is a multiple of 2. So I might as well just leave this row as it is for the moment and use it as a helper row to clear this column. So I am going to be replacing row 2. So I start with row 2 and I ask myself, what do I have to add to -6 to get a 0? +6. How do I get a +6 from 2? I multiply it by 3. So we'll take row 2 plus 3 row 1, and we'll use that sum and do a replacement of row 2. All right, row 1 is going to stay the same. We're not replacing it. And now -6 plus 3 times 2 is -6 plus 6, of course, is 0. It's what we wanted. 3 plus 3 times -1. Oh, well, that's 3 minus 3. That's also 0. And here's the cream. K plus 3 times H is just K plus 3 times H. We do not even need to address the fact that this is not in reduced row echelon form in order to answer the question. You see, we don't even need to bother to have a leading one here. We know this is the pivot position. What we do see is that we have a row that could potentially be a row with 0, 0, and then something not equal to 0, which would be inconsistent. So we realize that in order for the system to be consistent, what do we need? We need this to be a 0. So we need K plus 3H to equal 0. In other words, K needs to be -3 times whatever H is. Okay? So, to answer the question, as long as K is equal to -3H, the system will be consistent. Now, that's okay even for K and H to be 0. These could both be 0 and we'd get 0, 0, 0, in that sense. But H and K might have other values, but no matter what H is, K needs to be -3 times H. And you could even generate some possible solutions for different values of H, but that's not really necessary. Our last example today is considerably more involved. And this now is coming from section 1.2 in the book. This is actually exercise, again, number 23. And let's take a look at this. The augmented matrix looks like this. 1, H, 2, 4, 8, K. Now, there are a lot of ways to peel an orange. There are a lot of things that you could do here. I chose to go ahead and switch these 2 rows only because I did the algebra without switching these 2 rows, and it got pretty gnarly. It's not pretty any way you go about it, but I decided I'd attack it again and just see if the algebra simplified down a little bit, and indeed it did. So my first game here is going to be to just interchange rows 1 and that's not a row 3, is it? It's a row 2. Okay, so now we're looking at this. And you can try it the other way and, and just explore the algebra that way. I'm going to now go ahead and get a leading one here. There are many ways to do this, but I'm going to change this 4 into a leading one. You could at this point clear this column by subtracting 4 times row 1 from row 2 and replacing row 2 with that, right? But I'm going to do this. And if you work it out a different way and it looks significantly nicer and more elegant, by all means, submit it to me. So we're getting, of course, 4 divided by 4 is 1, 8 divided by 4 is 2, and K over 4 is our last entry here. Second row has not changed. And now, of course, we're going to clear this column because we have a pivot. We want to clear underneath that A11 position, clear the column. And the way that we'll do that is we'll take row 2 minus row 1. And of course, replace row 2. So row 1 is not going to change. But row 2 now is going to be 0, h minus 2 times, just h minus 2. And then we're going to have 2 minus k over 4. Okay, let me line this 2 up a little bit nicer with the, get the A12 entry and the A22 entry lined up. Okay, so here we have this. All right. Now, this is not necessarily pretty, but we can see something. See, we know to watch out for a row with zeros and then a non-zero. So either h minus 2 is going to be a 0, in which case we have to deal with consistency, or it's not. In the case that h minus 2 is 0, in other words, h is equal to 2, two different things could happen. When h is 2, we get a 0 here, and then this whole row could be all zeros, in which case we're going to have a free variable and infinitely many solutions. Or when h is 2 and this is 0, then it might be that k is a value so that this is not 0 and we get no solution. So we can see right now that h equal to 2 or not equal to 2 is going to matter. So let's explore if h equals 2. What could happen? Okay. So if h equals 2, then what do we have? We have 1, 2, k over 4, 0, 0, 2 minus k over 4. And then there are two cases. Okay. If 2 minus k over 4 equals 0, we have a consistent system because we'd have a row of all zeros, and that is not a problem. It just means that we're going to have a free variable because now, having a row of all zeros does not always mean you have a free variable, but it does here because we have two unknowns and we have two rows, which means we have two equations. If the number of rows equals the number of variables, and you have a row of all zeros, one of those variables is going to have to be free. If you have more equations than unknowns, then you can afford, in some sense, to have a row of all zeros and still not necessarily have a free variable. But because we have two variables, x1 and x2, and we have two equations, two rows, making a row of all zeros guarantees a free variable and infinitely many solutions. So let's just solve. So what is k in this case? All right, so we just, bring the k over 4 to the other side as a positive k over 4, and then cross multiply by the, multiply both sides by the 4 or cross multiply, and we get that k is 8. Okay, so for h equals 2 and k equals 8, okay, we get this. 1, 2, 8 over 4 is 2, 0, 0, and of course, 0. And that is a system that we can reconstitute right now. Because it's now in row reduced echelon form. There is only one leading one, okay? So this says that x1 plus 2x2 is equal to 2. In other words, our solution looks like solving for x1 in terms of our free variable. x2 is free, right? Because the column for x2 has no leading 1 in it. So x2 is free. x1 is 2 minus 2 times x2, whatever that is. So we have infinitely many solutions. When h is 2 and k is 8. All right, now we identified that, this quantity right here, the A2 position being 0, makes a difference in terms of consistency. And we have decided that when h is 2, we do get a 0 there, and only when k is 8 do we get a consistent system. And in fact, we have infinitely many solutions because we have the free variable x2 when h is 2 and k is 8. So we might as well now go ahead and address what happens when h is 2 and k is not equal to 8, because that's going to be our case when we have no solutions. For h equals 2 and k not equal to 8, just make sure we can see. There, this is what we're working at. We get this, okay? K is not 8, so we've got 1, 2, and whatever k over 4 is, okay? It's not going to be 2. 0, h is 2, so of course we're still getting the 0 there, and here we have 2 minus k over 4. And this is also not 0. So let's just write that down. But 2 minus k over 4 is not 0 because, I'll use b/c for because, k is not equal to 8. And this is an inconsistent system. And there is no solution if h is 2 and k is anything but 8. Okay. Now, things get interesting when we try to actually get a look at the solution when h is not equal to 2. Let me just make sure you can see this. Okay, because this is where we left off. All right, so if h is not equal to 2, then let's just write this down and let's see if we can get that in reduced row echelon form doing some algebra. So what we have is 1, 2, k over 4, 0, h minus 2, and 2 minus k over 4. And again, you can explore other ways to get a echelon form. This is echelon form. Okay? You have a pivot here and a pivot here, and we can march down and to the right. And under any pivot that has rows below it, it's all 0. So this is echelon form, even though it's not reduced. It's enough for us to see what's going on. Now we'd like to go ahead and get reduced echelon form, so I'm going to start by trying to get a 0 here. Okay. Did I say 0? What did I mean to say? That's right. I don't want a 0 here. I want a 1 here, a leading 1. So I'll just divide row 2 by 1 over h minus 2. That needs All right, so 1, 2, k over 4. Here, 0 divided by h minus 2, and h isn't 2, so this is not 0 we're dividing by, of course, is 0. H minus 2 over h minus 2 is 1. That was the point. And now we've got kind of a messy little situation. I'll just write it down like this. 1 over h minus 2 times the quantity 2 minus k over 4. That's our A row 2 position 3 entry. Okay, so let's simplify. That's kind of a mess. Let's see if we can simplify that A23 position. Okay, so A23 as it stands right now is 1 over h minus 2 times the quantity 2 minus k over 4. Okay. Hang on. Yeah, okay. Well, there are a couple of different ways to do this, but yeah, let's attack it this way and see what happens. Okay, so we have, let's see, 2 over h minus 2 minus k times 4 over 4 times h minus 2. And we can get a common denominator. All right, so 4 times h minus 2. Now, 2 is already over the h minus 2, so we simply have to multiply it times the 4 to get 8. K is already over the common denominator. And is that any better? Yeah, it's a little bit better. Let's see what happens now. A little bit worried, but let's see what happens. Okay. 1, 2, k over 4, 0, 1, 8 minus k over 4 times the quantity h minus 2. Okay, so why am I worried? Because we still have work to do to generate an actual unique solution. So now we need to clear above this leading 1. And that means we're going to use this row 2 as our helper row, and we're going to replace row 1. We're going to take row 1 minus 2 times row 2 and use that sum to replace row 1. Row 2 is not going to change. I'll just go ahead and write down row 2 the way that it is right now. All right, 1 minus, 0 times I don't care, 2 times, so it's going to be 1 still. 2 minus 2 times 1, that was the whole point, clears that. The A12 entry is 0. Now we have to deal with this. This is a mess. All right, so it's going to be row 1, which is k over 4, minus 2 times this row 2 entry. All right, so the 2, I'm going to write it one time, the whole thing, just for the sake of notes. But most of you are already canceling this 2 up top with the 4 down here in the denominator and simplifying that. All right, so let's simplify this. See, just the same way, maybe I'll use green here. Just the same way that we looked at this A23 entry. Yikes, it was a mess. Now we're looking at the A13 entry. Yikes, it's a mess. Let's simplify it. Okay, so I'm going to just do one step right away. I'm going to cancel the 2 up top with the 4 down here, and we're starting with k over 4 minus 8 minus k on top over 2 times h minus 2 on the bottom. Did I do that right? I think I did. All right, now I'm going to get a common denominator of 4 times h minus 2. Oh, that looks familiar. That's the common denominator here. Okay. All right, so k is already over the 4, so we have to multiply it by the h minus 2. 8 minus k is already over 2 times h minus 2. We simply have to multiply it by 2, right? Because we're going to be, and we still have this minus here, so we're going to be careful. We're multiplying by 2, but then we'll distribute this negative. All right, so what do we have? We have k times h minus 2 plus, just distributing this negative across here, 2k minus 16 over 4 times h minus 2. Yikes. And there's no h minus 2 to factor out of this term. Otherwise, wouldn't that be nice? But the h's are not going away that quickly. What we can do, though, is we've got up top, if we distribute this k across the h minus 2, we do have hk minus 2k plus 2k, at least the 2k's go away, minus 16 over 4 times h minus 2. I think that's about as nice as it's going to get. All right. So now let's just take a look. This is this case of a unique solution, all right? H was not 2. Okay, so let's just recall. H is not equal to 2. And now we have this expression. Here we go. Let's just write it down. Got our row reduced, completely reduced echelon form. A13 is now not so bad. It's not beautiful. It's HK minus 16 over 4 times the quantity H minus 2. And then our A23 entry is 8 minus K over the same denominator, 4 times H minus 2. So we get a unique solution, right? As long as H is not equal to 2, our unique solution looks like x1, x2 equals HK minus 16 over 4 times H minus 2, comma, 8 minus K over 4 times H minus 2. Okay, and that's for H not equal to 2. And you can see H cannot be 2 and have this be a defined quantity because we can't divide by 0. So I hope that you have enjoyed and learned something, and do realize that, yeah, the algebra can get a little sticky, but, you know, doing algebra is sort of like eating your vegetables. It's good for you. Thanks for watching. See ya in class.